All right, let's jump right in. Today, we're going to pull back the curtain on one of the most powerful and honestly most important ideas in all of computer science, the graph. It's this invisible network that's shaping our digital world in ways you probably don't even realize.
Okay, so let me start with a question for you. Think about your friends on social media, the billions of websites out there, or even just the route you take to get to work. I mean, on the surface, they seem like totally different things, right? But what if I told you they all share the exact same fundamental structure?
Well, it's true. The answer is that they can all be mapped out and understood using this one surprisingly simple idea. It's this concept that secretly organizes everything from our social lives to global logistics, and it's called a graph.
So, let's break this down. The word graph might sound a little intimidating. Maybe it brings back bad memories from math class, but trust me, at its heart, a graph is built on just two core components that are incredibly easy to wrap your head around.
And that's literally it. Seriously, a graph is just a bunch of dots, which we call vertices or nodes, and the lines that connect them, which we call edges or links. That's the whole thing. A person can be a node, and a friendship is the edge. A city can be a node, and a road is the edge. It is just a perfect, super flexible way to represent any kind of relationship. Now here's where it gets really clever. We can model all sorts of different relationships just by changing the rules for these edges. An undirected graph, for example, is like a two-way street. Think of a Facebook friendship. If you're friends with someone, they have to be friends with you. The connection goes both ways. But a directed graph, that's a one-way street. Imagine one web page linking to another. Page A can link to page B, but that doesn't mean page B has to link back. This simple little difference between two-way and one-way connections is what makes graphs so unbelievably powerful.
Okay, so we've got this really elegant idea of dots and lines, nodes and edges. But how does a computer, a machine that just thinks in ones and zeros, how does it actually see this map of connections and do something useful with it?
Right, you can't just shove a drawing into a computer's memory and expect it to work. We need a way to translate these visual connections into a language the machine can process. And to do that, we basically have two main methods, and each one comes with its own pros and cons.
So here we see the classic trade-off. First, you've got the adjacency matrix. You can basically think of this as a giant grid or a spreadsheet. It's super fast to check if two nodes are connected. You just look at the box where they intersect. Simple. The downside, it can use up a ton of memory, especially if you have a lot of nodes but not that many connections. Then you have the adjacency list, which is way more space efficient. It basically just keeps a list for each node of only the other nodes it's connected to. The compromise here, it's just a little bit slower to check for a specific connection.
And this quote right here just nails it. The best choice really depends on what the graph looks like. If your graph is sparse, meaning lots of nodes but relatively few connections, kind of like a social network, the adjacency list is the way to go. It saves a ton of space. But if your graph is dense, where almost everything is connected to everything else, then the raw speed of that adjacency matrix might be totally worth the extra memory cost.
All right, enough theory. We've talked about the what and the how. Now for the really fun part, the why. Let's look at how this simple idea of dots and lines powers some of the most critical technology we use every single day. And I mean, it's literally everywhere.
You are constantly, and I mean constantly, using graph algorithms. When you ask Google Maps for the fastest route, that's an algorithm called Dijkstra's running on a massive graph of roads and intersections. When LinkedIn or Facebook suggests someone you might know, that's them analyzing your social graph. And, Google's entire search engine was built on an algorithm called PageRank, which basically treated the whole internet as one giant graph to figure out which pages were the most important.
But it goes way beyond just the internet. This is where it gets kind of mind-blowing. In biology, scientists are modeling how proteins interact to discover new drugs. They find a specific pattern of connections, and bam, that could be a new way to fight a disease. It's a total game changer. Or think about cybersecurity. They map financial transactions as a graph to find fraud rings. They look for these weird, tight clusters of connected accounts that no human would ever be able to spot. It really is a universal tool for understanding any kind of complex connected system.
So once you start seeing the world this way, through the lens of graphs, you start to realize these structures aren't just in our computers. They are a fundamental way of describing how pretty much everything around us is connected.
So if there's one thing to take away from all this, it's this. Graphs give us a language to talk about connections. It doesn't matter if those connections are between people or places or ideas or even molecules. Understanding the network, seeing the shape of the relationships, that's always the first step to making things better, to finding new discoveries, and to uncovering those hidden patterns that are running our world.
And that really leaves us with one final, pretty exciting thought. So far, we've used graphs to map the networks we can already see. But the real frontier, the truly exciting part, is using them to find relationships we never even knew existed in the first place. So the question isn't just what we can do with them, but what new, hidden connections will they help us discover next?